Hey! I'm Zach. We're here to talk about characterizing thermal effects and reflective distance sensors. Let's get going. Okay, basically, to start off, we want to know the distance between two things. This is important in manufacturing, the automated kind. This is important with robotics, and sensors are a really good way to find out. There are heaps of different types of sensors, but I'm just going to run you through a couple that are used commonly in this sort of situation. We have laser interferometers. They're really good, but often they're really expensive, and things like dust can get in the way and screw up what's going on there. So we don't want to. Sometimes you don't want to use them. Magnetic sensors, again, really good. Again, can be expensive. Sometimes there's a bit of a problem here. Electronics and stuff emit a magnetic field. That can get in the way. That's a bit of a problem. So sometimes these are unsuitable. Reflective distance sensors. So this is what I'm going to be talking about. This is the Osram SFH9206. You don't have to remember that. Basically, it can be a really good compromise between price and performance. They don't have a lot of things that don't have a lot of problems with them, but I'm going to talk about a couple today. And they work by shining out an infrared light at a reflective surface, which is then reflected back and received by a photodetector. The photodetector can basically determine how far away the thing is. So, moving on. What's the biggest problem here? Thermal drift. Basically, you try and use this thing for a while, it's going to get hot. The results are going to go wrong, and you don't want that at all. So this prevents its use in these sort of high accuracy applications that I was talking about. And another big problem that's going to get in our way is the temperature isn't able to be measured. The thing is so small and compact, it's really good for certain situations, but unfortunately that means the temperature is not able to be measured. The junction temperature, it's too deep in the case, it's not going to happen. So we're going to find a way to do that. Basically, like I said, we've got to find a way to determine the temperature. And if we want to stop this, we've got to characterize how it behaves under increasing temperature. We've got to make sure the temperature is the only thing that's going wrong. There could be other things going wrong with this sensor. And basically, assuming the temperature is a huge impact, which I'm hypothesize that based on my data, fairly certain it is. I'm going to suggest a way. I'm going to try and find a way to minimize this if I can. So moving forward, boom. We got research, we got MATLAB modeling, I did experimentation and analysis. These are the 4 parts of my project, and each part has a sort of equal weighting onto the results. So research, we split it up into our LED part and our photodiode part because they're the 2 parts of this sensor. Basically, the LED is made out of gallium arsenide. This means it's going to put out 950 nanometer wavelength, a wavelength of 950 nanometer light. It's well in the infrared spectrum, and we know its voltage decreases with increasing temperature. We've got the photodiode. This is going to be treated as a phototransistor paired with a bijunction transistor. Voltage could decrease or it could increase. We're not quite sure at the moment. The literature is all over the place. Some places say the gain term is going to be constant, whereas others say it's going to increase and others say it's going to decrease. So we're going to talk about that a bit further later. But let's get started. We've got to model the temperature. Before we can do anything, we've got to find out how hot this thing gets. So that's what this top equation is going to do. You don't need to know too much about it. Basically, we're determining the efficiency of the diode, and based on an assumed efficiency of this diode, we're going to determine how much power is going to the heat. And using this RTH term, we can determine how much of that power is going to correlate to how much of a rise in temperature. So assuming a 30% efficiency, we're not going to see more than 5-degree rise. Based on its small size, we can assume that the efficiency is a little bit better than that, but just to keep it conservative, we're gonna say 30%. And it's not going to rise more than 4 to 5 degrees in that case. And as you can see, there's an I term there, so it's dependent on how much input you put into this. But at its max sort of value, it's not going to go over 5 degrees. You don't have to worry about that. How does it affect the LED? Well, like I said, the power is going to decrease. That's what the literature says. Here's an equation that we can use to determine sort of, the change in temperature that we're going to see with that sort of power decrease. With the voltage decrease, since we're using a constant current, it allows us to easily measure the voltage. So that's cool there. And our temperature value, we got this one here. So basically, the temperature is what it was plus the new change, plus the change in temperature. And if the problem with this is that we're going to need an initial temperature term, so you're not going to get out of measuring the temperature, but you can measure the ambient one, and it is possible to be measured. So that's going to be good. We can work with that. And here you can see we just got a graph. We can see how it clearly is decreasing with our temperature, and it's not a lot. It's only about a millivolt per degree. It's very small. It's a very small decrease. But when it comes to high tolerance situations, that 5 millivolts is very important, and it can significantly affect the results what you get. So, how are we going to model the output? Well, we've got this term here. K is meant to be constant, RC is going to be constant. B is beta is the gain term, which we're not sure yet. We're going to see how we go. And we've got ILED XPT on TC, which is related to the LED. So we're just going to start. We're just going to assume that's the only thing that's going to decrease this the sensor's output. This is the only thing that's going to be affecting it. This is the only thing that's going to be changing it. So based on that, we're going to see hopefully a decrease in the sensor output because the power of the LED is decreasing. Make sense? Power decreases, less light comes into the detector, and the output of the detector just decreases. It sees, oh, well, look, it's a bigger distance. So, cool. So, let's do some experiments. Let's see if I'm right. I don't know, I could be wrong. So basically, I chucked in a constant current source using LM317. You can have, it's a voltage regulator, and by adjusting the resistance, you can regulate the current. So that's real cool. To measure the voltage, I use the Picolog ADC24. Real accurate, it's nice. Took values every 100 millivolts, every 100 milliseconds. So I've got 10 readings a second. So we got some fairly precise readings there as well, because that can measure up to 0.01 of a millivolt, I believe. We did an unheated test just to confirm what was going on, and we did a heated test to test that thermal drift over a larger range. So, in our unheated test, we saw a rise of 2.96 millivolts and a temperature rise, which correlates with a temperature rise of around the same amount of degrees. The detector actually rose here, so I was a little bit wrong there. There's some other terms coming into effect, so we're going to discuss those in a little bit. And I found a much smaller thermal drift than other users. Other users were experiencing up to 100 microns of change. I only experienced 3. So that shows that maybe a constant current source has affected how this LED has changed, because the current was one of the major terms in the decrease of the LED power, changing that sort of thing going on there. So this is what we're going to see. As you can see, this is versus time, so it's your output versus time, and most of the heating effect is happening within the first 500 seconds. So if you just want to get out there, you don't care too much about your accuracy, but you'd like to decrease thermal drift if you could, leave your sensor on for 10 minutes and then start your recording. You should get much more accurate results, and you will hopefully be able to get that sort of accuracy you need, but you won't have to play around too much with this stuff like I am. So against our predicted temperature, we see a fairly linear trend. Unfortunately, over the higher degree, our models say it's probably not going to be linear, but it clearly shows that there definitely is some relationship between temperature and our output. So that's good to see. Good to know that I'm right. It's always good to be right? Moving forward. So what about our heated results? Well, basically, these much larger error. Boom! Thermal drift is a problem. I mean, that's not a good thing, but from my research, it's a good thing. So changing current. By changing the current, I input 4 milliamps. I put in 8 milliamps. No different in the LED but drift behavior. The models support that. There's no difference there, so don't worry too much about that when you're focusing on the LED. And changing the distance had no effect. Cool. Moving forward. This is what we're getting. So as you can see here, this is the final output. I've got a close and a far mirror. They're pretty much identical. They start around the same value. They end around the same value. A little bit different, but you're going to see the same sort of trend, the same amount of drift. Whereas when you use the 4 milliamp, you're going to see a much larger drift despite the LED remaining the same. So we're going to talk about that soon as well. Analysis. So we got an R squared value of 9999. Cool. There is definitely some thermal drift. The thing is getting hot. And my model predicts it really, really well. So that's awesome. The sensor model, on the other hand, not working. I said it was going to go down. It's going up. So let's talk about that. Must be the gain term. Again, this is just showing you how good my model for the temperature is, how well it works. Basically, we've got a little bit difference here. So the model predicts it a little bit higher, and that's likely because I'm measuring it against oven temperature. So the oven temperature was you got a sort of lag there as the sensor was measuring the oven temperature, but then we've also got the temperature of the actual sensor, which is producing its own heat as well. So we've got to take those into consideration. But we can see that we're getting a very good prediction of temperature here. So I'm going to adjust this model now. It's not working. How are we going to change the sensor output? Well, we've got this gain term, and there's factors influencing it, like A, B, and C. Now, the problem with A and B is that as a mechanical engineer, I can't quite understand them. I'm not going to get my head around them. That's a shame. C, on the other hand, I won't be able to quantify it. The research is out there, but there's nothing that's going to let me quantify this term. So we're going to find some other way to do what we're going to do, okay? Let's move forward. Gain term. Well, using the data and adopting our previous equations, I found this term to see how beta changes the gain term with respect to itself. And based on our data, we've got this term, and we can see it changes by an exponential growth model. So it's growing. It's growing at an exponential rate, which is fantastic for us. It means we can model it. We can find an approximation. So we can AE to the CT is a good approximation, provided we have the right A and the right C terms. So chucking this in, these are the same sensor outputs as we saw before. We're getting some pretty good overlap here. We're getting something that's really going to be able to predict what we're doing. And although it's not based on that A, B, and C term we had, it's still going to be able to get use and help other people who want to use this sensor reduce the effects of error in the future. So how will we reduce this error? Well, although I haven't completely reduced the error, I created a proof of concept model, and error has the potential to be reduced by at least 90%. And is really good because it's working across all currents and distances. I haven't put too much into this right now, but going forward, it definitely looks possible that we're going to get at least a huge amount of error reduction. So this is what we're seeing on our far mirror 13.1 milliamp thing. So I don't know if you remember, but we were seeing about 30 millivolts of variation in that. Here, this has been reduced to about 3, and the max error is at the beginning. So, and the good thing is for this error reduction value, the A and the C terms in that gain term are really easy to calibrate. C is always set to 0.005, and the A term can then be determined based on the initial values, which results in a sort of error reduction like this. And you can be assured that you're going to reduce most of the effects of ambient temperature. Basically, why is this important? Why does anyone care about this sensor? Well, look, we can use it in high tolerance fields now. You can use it in automated manufacturing. You can use it where a laser interferometer is too expensive for you. You can use it where you're around electronics and a magnetic sensor is going to spaz out. You can use it when you want to get your robot to pick up things. And when it's picking up things, it has to be down to, high accuracy. If it's trying to pick up very small objects. It offers a package. This sensor offers a package that others don't. It's such a small package, and it can be used in such high tolerance applications. It's low power, and there's all these things that make this sensor really good, that we can improve its accuracy going forward is a huge boost. So finally, basically, distance measurements are important. This sensor produces a good option, especially once the thermal drift is eliminated. Its behavior can be pretty easy to characterize through this set of equations, and I think that there's the error can definitely reduce. I've got a proof of concept model, and it's definitely working out. We're getting up to 90% error reduction, so that's fantastic. Here's my references. Thanks for watching, guys. I really hope you enjoyed it. If you have any questions, feel free to ask. Cheers.